Good afternoon. So I'd like to talk to you this afternoon about a Ka-band PA module that we put together using some low-cost surface mount packaged GaN components. So, as most people probably know, GaN technology is really the lead in solid-state technology for power amplifier ICs. It has a very high power density. It's more expensive than gallium arsenide per unit area, and so we developed a PA for a client, CML Micro as it happens, and that was a composite IC which had a small GaN die, keeping the GaN area as small as possible to keep costs low, and an IPD, an integrated passive device. And I'll show you a little bit more detail about that. So the Ka-band module that we put together, it operates between 28 and 31 gigahertz, got an output power of about 17 watts at 28 gigahertz. And I'm going to tell you a little bit about the IC and also explain about the PA module, how we put it together, and show you the measured performance and some thermal photographs. So we had the two die here in the package. Let me see if I can get a laser pointer on here. That doesn't seem to work too well. So what you can see here, I'll just have to wander over and point. These are the active devices, and what you can see, these are physically large devices, and this creates some design challenges, and I'll come on to that. But it was required to keep the device size down, to keep the cost down. And here, on the integrated passive device, we have the output bias Ts and also some matching. Now, this technique is used quite a lot at lower frequencies, but it's not often used at higher frequencies because there's quite a challenge in getting this interface just right. Now this is a 4mm by 4mm package. We have a custom lead frame here, you can probably tell from the pinout. So, I mentioned that we had these two output devices which were large. And indeed they were so large in terms of gate width and number of fingers, they exceeded the validity range of the PDK models. And you have to be careful when you do that because the accuracies of the models start to drift. But we had a very demanding client who insisted on having the die size very small. And so we said, well, okay, we'll give it a shot. So we got some sample transistors, close as we could to this size, and we measured them, small signal and large signal, and we looked at how far out the model was, and we made some adjustments for that during the design process. We also had to be very careful with simulating the die-to-die transition. So the impedance at that point at the output of the GaN device, that's lower, it's lower than 50 ohms. And what this means is that the impact of any inductance is more significant, and the impact of any uncertainties in that inductance is more prominent. And so we had to spend quite a lot of time simulating that transition from die to die and making sure we had all of that correct, and of course simulating the package transitions at input and output as well, because what we're ultimately interested in is the performance of the packaged surface mount component. This is the packaged PA on an eval board. So this is the module we put together. This was kindly donated to us by CML Micro, who we did the original PA design. So you can see there's a thin substrate there, and that helps keep the grounding inductance low, which is very important at millimeter wave frequencies. And it also helps you keep the thermal resistance low. We've got a copper carrier there for rigidity and for thermal heat sinking. And so we got this so we could do some measurements, so we could try things like the decoupling arrangement, make sure we weren't doing anything that upset the IC, before we put together our module. I've got a few graphs showing the performance of the package part. These are some S parameters. You can see the gain is about 15, 16 dB in the 28, 29 gigahertz band. Rolls off a little bit by 31 gigahertz, but still about 14 dB. And reasonable matches input and output. And this is the power compression performance, and it varies across the band. It's about a little over, it's about 4 watts, a little over 4 watts, 36 dBm or so at the low end of the band, and increasing higher, sort of above 37 dBm at the higher frequencies. Oh, this was measured pulsed, 100 microsecond pulse width, 10% duty cycle. I've done some, or the team who put this together did some CW measurements for the full module, and I'll show those. This is the PAE, also some variation across the band. Best PAE on these plots is at 29 gigahertz, which is about 27% when operating saturated. This is an IP3 graph. I put this in just because I had it. We've not measured IP3 at all for the module. That wasn't something we were aiming to do. We were just really trying to demonstrate how we could generate a good amount of power using some low-cost surface mount ICs. And this is just a summary of the measured performance of the IC on its own, the packaged 2-die IC. And you can see the gain, as I said, 16, 17 dB at the low end, in the sort of 27, 29 gigahertz range, rolling off a little bit at the top. PSAT, 36.7 dBm at the bottom, but creeping up to above 5 watts at the top half of the band. There's some other specs on there, IP3 and ACPR. We didn't do any ACPR measurements for the PA module. It's something we could do at some point, but we haven't at this time. So this is a block diagram of the module. Now all the green blocks are splitters. So we looked around at the splitting, what we could get for splitting networks, and what we did in the end is we printed a splitter. We just did a Wilkinson splitter, and we didn't do any resistors. So you can get away without the resistors as long as you're driving in phase and things don't go wrong. You drive them in phase, then you don't need the resistors, and you end up with something that's very cheap and very low loss. But it won't work so well if one of your amplifiers were to fail. It wouldn't be a benign, graceful failure. But for our needs here, it worked very well. The red blocks are gain compensation networks, and they're just printed filters. And what we're aiming to do is flatten the gain versus frequency response. So we're using the same amplifier in the driver stage and the output stage. And so the gain response will multiply up. And so we put these gain compensation, they're just printed structures. I'll show you what they look like in the photograph. And the aim was to flatten the gain versus frequency response. So we've got 4 PAs in the output, that's all combined, and we've driven them by 2, and we used 2 devices rather than 1 because we wanted to make sure it was the output stage that was compressing, and you'll see this in the thermal images that are coming up shortly. That was indeed the case, and maximise the amount of power we could get out with still a sensible amount of gain. So, choice of the PCB substrate. So we chose a Rogers PCB substrate, a 6035 HTC, and we chose this because it has a good thermal conductivity. We went for a thin thickness, 10 thou, quarter of a millimeter, and this gives us low grounding inductance. It gives us low dispersion, and it also helps us keep the thermal impedance lower as well of that PCB material. Under the QFN paddle, we use solid copper vias because that helps get the heat out. And we used an immersion silver finish. And that immersion silver finish means that you can avoid nickel. And a popular finish is ENIG, but that has nickel in it, and nickel tends to have a lot of loss. but a immersion silver finish gives you something that's solderable, but has much lower loss. There's a reference, I think reference 3 in the paper, which points to a paper that gives lots of useful guidelines for the design of millimeter wave and microwave PCBs. So this is the simulated performance, and you can see the red trace, the gain response there. It's considerably flatter than you might expect for 2 of those initial ICs cascaded. And this is all EM simulated, all of the printed structures, the splitters and the gain compensation networks, all EM simulated. And this is what our module looks like. Now, you can see here, this very small structure. Things are very small when you're up at millimeter wave frequencies. That's the input Wilkinson splitter. And you can see here, these are the gain slope compensation networks. So there's a radial stub on the end there, and that gives us a broadish band short circuit. And then we've got stubs on there. So it's effectively a printed inductor to ground. And this was a high pass filter, and it helped flatten the gain versus frequency response. And at the top there, you can see there's a little through line. And this just allows us to take out that connector and that bit of track. And then we can reference the power to that point where we've combined the 4 PAs. So we're really getting then a good comparison with a commercially available single device, which you might get in a flange mount package. So we can compare this approach of using multiple lower cost, lower power devices with a single higher cost device, which would probably be in some sort of flange style package. These 3 black blocks are where we plug in the DC bias. We didn't use a multi-layer approach because we wanted to keep it simple to prove what we could achieve using this approach. And we've got millimeter wave coaxial connectors at each port. So this is the thermal image of it at quiescent bias. So we're running each of the ICs at 100 milliamps quiescent bias, 27.5 volts on there. So each device then is taking 2.75 watts. We've got it on a nice base plate, and you can see they're all running quite cool. And you can see 2 things. It doesn't get too hot, about 34 degrees centigrade. Now that's the top of the package. Obviously the junction will be a bit hotter, but this is a very useful indication. We can also see that there aren't any hot spots. This green band here is just one of the biasing wires going over the IC. But all of the ICs are running at the same temperature. There are no hot spots, which means we've got good void-free solder attach. This is a measured to model performance. Now that's the measured performance I showed you before. Is the simulated performance I showed you before are blue traces. The green traces are the measured performance. So you can see we've got more gain, a little more gain slope and a little bit of gain ripple that we never had in the simulations, but we've got those in the measured performance. But we're seeing that the gain is about 29, 30 dB at the bottom of the band, rolling off to just under 25 dB at 31 gigahertz. And this is the power compression. This was measured pulsed with 100 micron a second pulse width and 10% duty cycle. And we ran it up at 28, 29, 30 and 31 gigahertz. And those are all of the traces. So you see nice and linear as you'd expect at the bottom. We take it up to saturation. And to say you're trying to read across on the graph, I've tabulated on the left the measured power at PSAT. And there's a little bit of variation of the band. And you see actually the highest power frequency happens to be 31 gigahertz, where it's 18.4. But I just quoted the 17 watts at 28 gigahertz. It's a useful frequency that people are interested in. And these power measurements are referenced to that output of the printed 4-way combiner. So this is a intra-pulse measurement, so you can see it switches on nicely and has quite a nice flat top with no droop off there, indicating that we're not seeing much in the way of thermal effects. The power there you can see measured at the bottom, 41.7 dBm, and that includes the loss of the output bit of track and output connector, which is about 0.6 dB, which takes you back to the 17 watts at the output of the combiner. So we take another thermal image now, and it's running at PSAT, so it's dissipating more power, so it's got a bit warmer. Everything's moving in the way we'd expect, but not too warm. It's about 36 degrees. And again, you can see the output devices are slightly hotter than the input devices, which is what we want. We also see everything is about the same temperature. We've got void-free solder attached, something we strive for, but you have to approach it carefully and work with the manufacturer to achieve it. And it also shows us that those PAs are all being driven at the same level as well. We've got a nice phase balance between them. So what we did next is we measured it CW, and we wound it up, and we got a little bit less power, as you'd expect. You get about a dB less power when you operate at CW, but it all works fine. It's nice and happy. And we left it on, we took a photograph. I've changed the colour scale a little bit here, but it's not bad. It's about 80 degrees at the top. Now, these devices have a maximum junction temperature of 225 degrees centigrade. So, you know, we're quite some way from that. You have to be careful with thermal images, because they will auto-scale. So if your hottest temperature is 20 degrees will be red. So you have to be a bit careful. So we adjusted the scale to give something sensible. So these devices are about 80 degrees. And again, you know, they're quite consistent very consistent from unit to unit. All looks to be behaving well. And we left it on, never burst into flames. That's always a result. And yeah, we were quite happy with that. So, to summarize, so we developed a Ka-band PA module using 4 commercially available SMT package devices, power combined. We used a laminate substrate on a copper carrier. We selected a thin substrate material for good microwave performance with a good thermal conductivity. We've got printed power combiners, which are all resistorless Wilkinsons. We've got some printed gain slope compensation networks. And we've shown you some measured results. And we can see that the small signal gain varies from about 30 dB at 28 gigahertz, dropping to just below 25 dB at 31 gigahertz. RF pulse power, it reaches a saturated level of 17.4 at 28 gigahertz. Some variation across the 28 to 31 band, ranging from 14.9 to 18.4. And when we run this PA saturated, we see the power drop by about a dB, because all the devices are all running hotter when running CW. The thermal images we took tell us that we've got a void-free solder attach between the base of the QFN package and the PCB material. And it also shows us that we're driving everything in phase, because all the temperature is the same, and the temperature looks a very comfortable level for CW operation. Thank you very much.